Today, we are going to talk about sequences and their notations. This is a skill that's normally talked about in college algebra, pre-calculus part 1, maybe pre-calculus part 2, but since we don't always cover this in all pre-calculus classes, and it's an important skill in both calculus and statistics, we're going to go ahead and talk about it in our prerequisite review videos that we do for those two subject matters. So we're just going to start by talking about some examples. We'll come back and talk about more specific examples of different types of sequences, but the first one we're going to look at is going to be about a medication. A patient takes a 30 milligram antibiotic capsule. At the end of that hour, the amount of antibiotic remaining in her body is only 90% of the amount in the beginning of that hour. The 30 milligram dose is taken at time equals 0 hours. How much of this dose remains at the end of 1 hour, 2 hours, 3 hours, 4 hours? So the amount at the end of the hour is 90% of whatever it was at the beginning of the hour. So if we had 30 milligrams at the beginning of the hour at t equals 0, then at t equals 1 at the end of the hour, we'd have 90% of that, or 27 milligrams. Then at the end of that hour that started with 27 milligrams, we'd be left with 24.3 milligrams. And then at the end of the next hour, we'd be left with 21.87 milligrams. And at the end of the next hour, we would have 19.68 milligrams. If you talked about exponential functions in pre-calculus part 1, this is going to be exponential decay. And it's going to look something like this, where it's coming down, down, down. Eventually, somewhere down here, it's getting close to y equals 0, but it's not ever getting there. Because if you take a fraction of a fraction of a fraction, you've still got something left, right? So it's based off of that. So we've got an ordered list, a well-ordered list where there's definitely a first number, second number, third number, fourth number, and so on, right? If we wanted to, we could throw the number 30 at the front of this list. I didn't do that though, because this worksheet is talking about that n equals 1 should refer to the first number in the list, n equals 2 to the second number, and so on. So I didn't really want to get into right now in this example talking about the first number being when time was 0. We'll come back to that later though. If you have a finite number of terms, like we only found the first 4 terms here, that's finite. We can list them all out and we can start, and then we have a definite stopping point. We can name all of them, right? Or we can have an infinite number of terms that makes an infinite sequence. And when we do that, we have the entire set of natural numbers, which would be the counting numbers, 1, 2, 3, 4, 5, and so on, or even the set of whole numbers. If we want to start counting at 0, we can do that 0, 1, 2, 3, 4, 5, and so on. And that, if we just go on forever in that pattern, is going to be an infinite sequence. It's a countable infinity, but it's still infinity. So because we can't always write out all the terms, we're going to come up with a notation instead to help us calculate the nth term. Just like we would use function notation to find all of the xy ordered pairs for any x value that somebody wanted to give us. Now our inputs are not going to be any real number, x. Now they're going to be a natural number that we're going to call n, and we're going to switch variables to denote that. We're also not just going to call it f of x, because we want to be clear that this is a sequence. So we're going to use the notation a sub n. So this is the nth term of the sequence a is defined by 2 times n, right? And this 2n is called the general term of the formula or the formula of the sequence. So we can stick in any n that we want to and calculate a sub 50 and find the 50th term of the sequence, for instance. So the 50th even number here would be 100. And they're just telling you that when we get out there and want to be generic, we can talk about the nth term, and it's going to be important to sometimes talk about that next term after the nth term. So we're going to call that the n plus 1th term. Okay, so this will be really important to look at these two terms later to decide if something is geometric when we get to that specific set of sequences later. For right now, though, let's just practice plugging in n values, natural numbers, for the index n and plugging it into the formula and calculating that term of the sequence. So we've got a general term of 2n minus 7. We're going to plug in our first n value of 1. 2 times 1 is 2. 2 minus 7 is negative 5. Then we're going to plug in 2. So our a sub 2 term is going to be 2 times 2 minus 7 is going to be 4 minus 7 is negative 3. Follow that pattern. 2 times 3 is 6, minus 7 is negative 1. Then 2 times 4 is 8, minus 7 is 1. 2 times 5 minus 7 is 3. It's pretty straightforward to go forwards like this. It's going to be a little trickier in a couple examples when they ask you to go backwards, but we'll get there. So this one is going to be 4 times 1 plus 2, 4 times 2 plus 2, 4 times 3 plus 2, 4 times 4 plus 2, and 4 times 5 plus 2. 4 plus 2 is 6. 8 plus 2 is 10. 12 plus 2 is 14. 16 plus 2 is 18. And 20 plus 2 is 22. That's a special type of sequence that we're going to be talking about later called arithmetic. And what's special about it is that there's a common difference that I can take 6 plus 4 to get 10, then add 4 again to get 14, add 4 again to get 18, and add 4 again to get 22. So whether that's a positive number or a negative number that I subtract, and the thing that's going to give away that it's arithmetic is that it's going to look like a linear equation that can be written kind of sort of in y equals mx plus b form. But this one is not like that. This one is nonlinear, so it's not going to be arithmetic. So we're just going to have to figure this one out. This is going to be related to powers of 3. 3 to the first minus 1, 3 to the second minus 1, 3 to the third minus 1, 3 to the fourth minus 1, 3 to the fifth minus 1. And this is going to be 3 minus 1 is 2. 9 minus 1 is 8. 27 minus 1 is 26. 81 minus 1 is 80. 243 minus 1 is 242. So now we're going to go the other way, and they're going to give us some terms, and they want us to find the general term through a process of what's called induction. Let's take a little bit of information that we know, and let's induce a pattern. So 4, 8, 12, 16, 20. We just talked about this exact one where it looks like we're adding 4 each time. So we're going to take 4 times 1 was 4, 4 times 2 was 8, 4 times 3 was 12, 4 times 4 was 16, 4 times 5 was 20. So we think the nth term is going to be 4 times n, and we're going to write that pattern a sub n equals 4n. Then they're going to give us 1 over 3, 1 over 9, 1 over 27, 1 over 81, 1 over 243. We just saw all those numbers that were in the denominator as the powers of 3 in a previous example, but they're going to write that out for us here, that this is going to be 1 over 3 to the first, 1 over 3 to the second, 1 over 3 to the third, 1 over 3 to the fourth, 1 over 3 to the fifth. So we assume the nth term is 1 over 3 to the n. There's other ways that we could write that as 1/3 to the n or 3 to the negative n. Those also work. So we'll talk about those more when we get back to something called geometric. So it's geometric sequence. Okay. Now let's have you practice and let's write the nth term. So this looks like 8 plus 8 is 16, plus another 8 is 24, plus another 8 is 32, plus another 8 is 40. So this looks like maybe this is 8 times 1, 8 times 2, 8 times 3, 8 times 4, 8 times 5. So 8 times 1, 8 times 2, 8 times 3, 8 times 4, 8 times 5, and we would assume that this would be 8 times n. So our nth term should be an equals 8n. Let's keep going. 1 over 4 to the first, 1 over 4 to the second, 1 over 4 to the third, 1 over 4 to the fourth, 1 over 4 to the fifth. So 1 over 4 to the first, 1 over 4 to the second, 1 over 4 to the third, 1 over 4 to the fourth, 1 over 4 to the fifth, 1 over 4 to the n. So we assume that our an is equal to 1 over 4 to the n. Again, you can write that as 1/4 raised to the n or 4 to the negative n if you prefer that. Those would also be acceptable. So that's all for this particular worksheet. Again, big idea is that finding the general nth term here is a form of induction where we were given less information than what we wanted to find. And being given the general term and wanting to find the specific terms here is a form of deduction where you were given big idea and find specific cases of it. So those are two ideas in logic. So we also deal with sequences in discrete math when we talk about induction and deduction. All right. We'll come back next time and we'll talk about some specific sequences.